Good morning. Today we can see a single degree of freedom system using a periodic loading calculate with a Fourier series. In the last video we saw the how modelizing the triangular periodic loading using the Fourier series. We remember, okay, the system using for the single degree of freedom system is a mass with applied force pt in direction x, and to this mass is applied also an dampened system and a spring k. You can remember the simple passage to calculate the second equation, differential equation of this displacement, m for velocity plus c, c is the damping coefficient for velocity, plus cap of stiffness of spring for displacement is equal of t. You can remember the periodic loading is a period load is a force of dynamic stress che ripete identically a regular time interval, and in this case we applied a triangular function. In this example, applied a triangular function similar of this. Okay, you remember the periodic function pt. You can modelizing this triangular force with the formula similar of O3 or 4, where n is the number of harmonic. We can this number we can vary values between 1 and infinity. Omega 1 star is the first harmonic frequency of load function equal to hp for TDP, where TDP is period of the load function, and omega n is equal to n for omega 1 bar. For undamped system, the total response produced in undamped system by each sine term of harmonic loading series given of this equation. The steady state response can be determined by omitting the transient term sino di omega t. Can rewrite xn equal bt bn divided for kappa multiply 1 for 1 less bn elevated 2 for sino di n omega 1 bar for the time t, where beta n is n omega 1 bar divided for omega. The cosine term is written in this way, so the total periodic steady response of damped structure we can express it in the following way, where the term the constant term at 0 k is is this value in the 4 in the 6 equation. For undamped system, to take account, so this is the equation for undamped system and the 6. We can write also the equation for the damped system, take account the damping in evaluating the response of a SDOF structure to a periodic loading. It's necessary merely to substitute the dampened harmonic response expression in the form of equation. So xt is equal of this two term. For undamped response, expression in equation 6 in equation 6, the total state response is given by this equation. We can convert this equation in exponential form. Remember, using the Euler form, where e elevate imaginary value for theta is equal to coseno di theta plus I imaginary value for seno di theta. So in this case the variable is the displacement x, so seno di x equal when I for e elevate x, when e elevate 1 x divided for 2. Similar formula, but this is the sen is the term imaginary, and coseno di x is not imaginary value. Okay, so in the real jump, so e elevate x plus coseno di x e elevate x plus e elevate less I elevate x divide for 2. By substituting a standard Fourier series, a periodical odd pt, you can express integrally in this way. The complex Fourier coefficient Cn are calculated using integration of a period Tp. So Cn is equal to 1 divided for Tp for integrate of this equation. To find the steady state response, the standard equation of motion for a damped and SDOF system is subject to a unit complex formula. So we can write Pt elevate I omega t. So assuming a steady state solution on the form xt equal h omega bar per e elevate I omega t, where h omega t is the complex frequency response. The first and the second derivative of this equation give the velocity and this acceleration. So we can put these three equations in the equation of movement. We can write this equation, and we can isolate h omega t. So h omega t is equal of 1 divided for less omega bar elevated 2 per m plus c omega bar for c plus k. Also in this way we can also in this way we can also write the equation x, take count of omega bar is equal to n omega 1 bar. So the equation 9 we can rewrite in this form, where beta 1 is omega 1 bar divided for omega. The equation set show che hn omega 1 is complex conjugate of hn omega 1 bar. Hence it is possible to express the steady state response of a SDOF system to the forcing function which represent each term of Fourier series. For the principle of superposition, we follow the total steady state response of the system to any period forcing function can write in this way, where hn omega 1 is given from equation 8 is this, and Cn is given from equation set. So let us substitute equation 9, equation 8, so xt is equal of this, and we can make this passage and arrive at x t equal h prime omega bar for x prime di xt. So h prima di omega bar is equal of this equation, x primo t is equal to ptk. It means when periodic force Pt is applied statically to SDOF system, the resulting displacement become x primo t, hence h omega bar can assume to be a magnification factor representing the complex ratio of steady state displacement to displacement with which result from the exciting forces applied statically. So the frequency h omega 1 omega contain information regarding the phase lag of the response with respect to the existing force function. The term h prima omega can write also as the vector sum of the real part r omega, imaginary part e omega, or in this way, where h the value the absolute value of h omega bar and phi r are the amplitude and the phase of response of xt of SDOF when it is excited by the simple harmonic forcing function ft equal a k for f primo t. So x dt is write in this way, multiplying both the numerator and denominator of 9 pi 1 des beta elevated 2 des 2 e beta xc, we can get in this way. The amplitude h omega is found to be in this phase a phase angle is this also equation. Okay, this is the theory. Now we can represent the equation of motion using Python code using the Fourier series. So we can see the code of Python to represent this case of triangular periodic load with the application of a triangular periodic load. So in the line 15, 16, 17 there is the import of a library. The first is the library numpy, where for numerical operation, array, handling, and a mathematical constant. The scipy.integrate.odeint code import odeint for solving the ordinary differential equation, a quad for numerical integration. The import matplot import the pyplot module for matplotlib for generate graphic visualization. Then there is the definition of triangular force with the Fourier series. We can study this equation in the last video, in the present video, where define a curve 1 t in function of time t of period t grande of the p. Define the function for the A0 term, and if t minor or equal of t divided for 2, check if the time is the first half of the period, and return this value, the 24 return this value. In the case is not this equivalence is not when t measure of t divided for 2, return this other value. After define curve 1c, define the function to calculate an, the part for multiplicate for cosine, the Fourier coefficient. So w W is equal to for pi grec divided for t, calculate the fundamental angular frequency. If t is minor or equal of t of a period divided for 2, constructed the basic triangular shape P1 exactly as defined calculate the fundamental angular frequency. Allora, here, okay, W define the fundamental angular frequency. After if constructed basic triangular shape exactly as above, and after return this value when t is minor or equal to t divided for 2, or a measure of this. After there is the curve 1s, is the term bn for the sin, and the logic is the same. Define omega and define return the value of p1 and p2 in these two cases. After the line 45 define the parameter of a system. So the mass apply this is 5 kilonewton for second elevated 2 divided for mass. K is the spring constant, kilonewton per meter. Zeta is the damping ratio, in this case 5%. P0 is a force of amplitude, 10 kilonewton. T force is period of triangular force, so is equal to second, and term stopped the number of Fourier term to 10. Include this. The derived variable is omega, the period, and the damping coefficient. After we pre-calculated the Fourier coefficient, so the value of A0, define in the line 66, 67, define the use the scipy quad to numerical curve 1, cioè a 0 numerical integrate to find the constant, the value of A0. A in P0 and term divided for B, initializing empty array of size 10 to store the AN and the BN coefficient. After there is the for in range 1 and term plus 1, loops for 1 to calculate the each harmonic coefficient, and calculate n1 n less 1 b n less 1. Called the integrate function quad, and called the function curve 1 coseno and curve 1 seno. Ips sub psi is value to calculate an error to calculate this integration. Okay, after there is a numerical integration setup, so define difference equation, define the system of the first order or the int. Xv is equal a z, pack the state vector z into displacement x and velocity v. F the force of Fourier t, call the Fourier function to get the force at the current time step. Dx dt, the first order define the derivative of displacement is the velocity. dv dt, the second order calculate acceleration to rearranging the equation of motion of m as for acceleration plus c for velocity plus k for displacement is equal of force. And after return the displacement and the velocity and the acceleration. Here you see the initialing the condition, the displacement, initial displacement of time 0 is equal to 0.0 meter, and the velocity is equal to 0.05 meter per second. The total duration to plot this value is 15 seconds. T equal NP range 0 to, so the T values 0 TF with and step 0.005. Here there is an integration of motion called the function odeint for the differential equation it will pass the initial value and the time t. In the z okay, x total equal 0 1, extract all the displacement velocity value from the solver out matrix. Okay, after steady state we can calculate the steady state and the transient displacement calculation, and x steady equal np1 like t for a0 divided for k is the static response to a term or zero term, and for n in range loops through harmonic to calculate the dynamic steady state response analytically via superposition. Omega equal n for 2 omega and omega t, the frequency of a current harmonic. Denominator refers for nf harmonic for these two equations. Here the response to cosine term and the response for sine term. The transient response is the sum of total response less steady state response. In this step we calculate in line 129 calculate the acceleration, the force and the force. Initializing f applied is equal in n0 like t plus a0, and make the loop for n in the range 1 n term plus 1. Calculate the omega n and the force in this loop. The acceleration is equal to total is f applied less c for v velocity less k for x total 2 divided for m. Individual resisting force is F spring is K for x total, F damping is S for the velocity. And after we can plot the result in the graph for the displacement plot, for the velocity plot, the acceleration, and also for the force plot, and save all in a file PDF. We can see, and is this where the first graph is the transition response in red, the red line. The steady state response is the black line, and the total response is the blue line, combination of the transient and the steady response. The total velocity is the green line, and the acceleration is the red line. Here there is the representation of force, where the line black is the triangular force load and applied all 2 seconds, and after there is the spring force in blue and the damping force in violet. We can also simulate this system. So here there is the mass where applied the Fourier triangular force. Here as change the displacement and the velocity, acceleration, the force in function of time. Here there is the table with there are the input value, the mass 5 kilonewton second per meter, the stiffness 100 kilonewton per meter, and damping coefficient is equal to 2.24 kilonewton second per meter. The force amplitude is 10 kilonewton, the force period t is 2 seconds. The Fourier term using is 10, and there is the displacement, initial displacement, and initial velocity applied for this system. Okay, thank you, bye.